Roald Hoffmann once said, "Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements, but of the infinite variety of molecules that may be built from them." Now, isn't that a fascinating prospect? It's like a universe of possibilities waiting to be discovered and understood. That's what chemistry is all about. In this video, we will delve into the basic concepts of chemistry, a subject that's not just about elements and molecules, but also about the transformations they undergo. This journey will lead us through the development of chemistry, its importance, the nature of matter, and more. We'll explore how matter is classified, measured, and understood. Every concept we cover, every term we define is a stepping stone towards a deeper understanding of the world around us. So, are you ready? Let's embark on this fascinating journey into the world of chemistry. Chemistry as we know it today didn't just appear overnight. It's a science that has been shaped and refined over millennia, beginning with the ancient civilizations. The Egyptians, for instance, were early pioneers, using chemical reactions to create cosmetics and perfumes. Fast forward to the Middle Ages, and we see the emergence of alchemy, the precursor to modern chemistry. Alchemists were driven by the desire to transform base metals into gold, and although they never achieved this, their experiments laid the groundwork for future discoveries. The Enlightenment era brought about a more systematic approach to chemistry. Scientists like Lavoisier and Dalton proposed theories about elements and atomic structure that still hold relevance today. The 20th century saw the advent of quantum chemistry and the unraveling of complex molecular structures. It's been a journey of discovery, of trial and error, of refining and redefining our understanding of the world at a molecular level. These historical developments laid the foundation for the chemistry we study today. Why should one study chemistry, you ask? Well, let's dive into that. Chemistry, in essence, is the backbone of our daily life. It's in the food we eat, the air we breathe, and even in the emotions we feel. Yes, love is all about chemistry too, but it doesn't stop there. Medicine relies heavily on chemistry. It's key in developing effective drugs, understanding how they interact in our bodies, and improving them for better health outcomes. In industry, chemistry helps create a vast range of products, from plastics to cosmetics and even fuels that power our cars and homes. And let's not forget the environment. Chemistry aids in understanding and tackling environmental issues such as pollution and climate change. It's central to developing sustainable solutions and cleaner technologies. So, you see, chemistry isn't just about elements and molecules. It's about life itself. Clearly, the importance of chemistry is immense and far-reaching. Let's turn our attention to matter, the stuff that makes up everything around us. Imagine the world as an enormous sandbox filled with countless grains of sand. Now replace each grain with an atom and you'll start to grasp the concept of matter. Matter is anything that has mass and occupies space. It's in the air we breathe, the food we eat, and even the thoughts we think. Matter can exist in a variety of states, most commonly solid, liquid, and gas. Each state is distinguished by the behavior of its particles. In a solid, the particles are packed tightly together and vibrate in place. Liquids have particles that are a little more free to move around, and in gases, the particles are spread out and move rapidly in all directions. But wait, matter gets even more interesting when we start to classify it. At the broadest level, matter can be classified into pure substances and mixtures. Pure substances, like elements and compounds, have a fixed composition. Take gold, for instance. Whether you find it in a ring or a gold mine, its composition remains the same. However, mixtures are a bit more relaxed. They can vary in composition. Think of a bowl of fruit salad. Each bite may contain different fruits, hence different composition. But we don't stop there. We further classify pure substances into elements and compounds, and mixtures into homogeneous and heterogeneous mixtures. Elements like gold or oxygen are substances that cannot be broken down into simpler substances by chemical means. Compounds, on the other hand, are substances composed of two or more elements in a fixed ratio. Water, for example, always has two hydrogen atoms for every oxygen atom. Finally, we measure the properties of matter to understand and categorize it further. These properties can be physical, like color, odor, or state, or chemical, like reactivity or flammability. By measuring these properties, we can identify, classify, and even predict how matter will behave under different conditions. Understanding matter gives us a fundamental understanding of the world around us. Opening. How do we measure matter in chemistry? Well, it begins with understanding both the physical and chemical properties of matter. Physical properties are those we can observe without changing the identity of the substance, such as color, odor, melting point, boiling point, density, and hardness. On the other hand, chemical properties describe the way a substance may change or react to form other substances. Now, when we talk about measuring these physical properties, we're referring to quantifiable characteristics like mass, volume, and temperature. Let's dive into these a bit. Mass is the amount of matter in an object, and it's measured in kilograms according to the International System of Units, also known as SI. Weight, however, is the force that gravity exerts on an object, and it's dependent on the location of the object in the gravitational field. Volume, on the other hand, is the amount of space that a substance or object occupies. It's measured in cubic meters in the SI system, but in chemistry, we often use liters and milliliters for convenience. Density is a physical property that shows the relationship between mass and volume. It's calculated by dividing the mass of a substance by its volume, and its SI unit is kilograms per cubic meter. Temperature is a measure of the average kinetic energy of particles in a substance. It determines the direction of heat flow from a region of high temperature to one of lower temperature. The SI unit for temperature is the Kelvin. Now, these measurements are crucial in the realm of chemistry, and they're made using a variety of instruments, from simple tools like rulers and thermometers to complex devices like spectrometers and chromatographs. To ensure consistency and accuracy across the globe, chemists use the International System of Units, or SI, which is a universally accepted method for expressing the amounts of key properties. Closing, accurate measurement is the cornerstone of all scientific discovery. Measurements are rarely perfect, and that's where uncertainty and significant figures come into play. Uncertainty in measurement is a concept that acknowledges the inherent limitations of any measuring device. It's the reason why we use scientific notation to express large or small quantities with precision. Scientific notation involves expressing a number as a product of a number between 1 and 10 and a power of 10. Now let's talk about significant figures. These are the digits in a number that carry meaningful information about its precision. There are rules to identify significant figures and different rules when you're adding, subtracting, multiplying, or dividing them. When adding or subtracting, your answer should have the same number of decimal places as the measurement with the fewest decimal places. When multiplying or dividing, your answer should have the same number of significant figures as the measurement with the fewest significant figures. Understanding these concepts helps us handle data in a meaningful way. Lastly, let's delve into dimensional analysis, a critical tool in chemistry. Dimensional analysis, also known as factor label method or unit factor method, is a technique that uses the fact that any number or expression can be multiplied by 1 without changing its value. It's a method of problem solving that allows you to use units to understand problems. You might think of it as a roadmap that guides you from the unit you have to the unit you need. Imagine we have a problem that requires us to convert meters to kilometers. The dimensional analysis would involve multiplying the number of meters by a conversion factor. In this case, 1 kilometer is equivalent to 1,000 meters. So, we choose a conversion factor that cancels out meters and leaves kilometers. The beauty of dimensional analysis is that it provides a systematic, foolproof method for ensuring that your unit conversions are accurate. It's a process that's based on logic rather than rote memorization, which can be a breath of fresh air in the often complex world of chemistry. But dimensional analysis is not just about converting units. It's also a powerful tool for solving complex problems. For instance, if you need to calculate how many atoms are in a gram of a substance, you would start with the mass of the substance in grams and use Avogadro's number, the molar mass of the substance, and dimensional analysis to find the answer. Dimensional analysis also helps in checking the correctness of a physical equation. If the dimensions of the left-hand side of an equation are the same as the dimensions of the right-hand side, then the equation is dimensionally correct. With all these applications, dimensional analysis is indeed a versatile tool in the field of chemistry. It's a method that cuts through complexity, turning what might seem like an insurmountable problem into a series of manageable steps. With dimensional analysis, we can tackle complex problems with ease. In the past 10 minutes, we've journeyed through the basic concepts of chemistry. We've seen how chemistry evolved and learned about its pivotal role in our world. We've delved into the very nature of matter, exploring its states, classifications, and properties. We've understood how we measure these properties, the significance of the international system of units, as well as the concepts of mass, weight, volume, density, and temperature. We've discussed the inherent uncertainty in measurements and the importance of significant figures. We've even touched on the mathematical operations involved and the process of dimensional analysis. Yes, it's a lot to take in, but remember, this is just the tip of the iceberg. There's an entire universe of molecules waiting to be discovered and understood. So, continue to explore, question, and learn. Remember, chemistry isn't just a subject, it's the language of the universe.